So a rational expression is basically just a fraction. Numerical fractions are just like a specific type of rational expression. In general, a rational expression is, so a rational expression is a fraction with polynomials in the numerator. And denominator. So we don't usually think of like a number as a polynomial, but like when a polynomial has a constant term, right? So like 4x squared plus 3x plus 2, like this is a perfectly acceptable term in a polynomial. And so it's actually a polynomial on its own as well. Like 2 is just a monomial. It's a one-term polynomial. And so when you have a fraction like 2 over 6, that's a rational expression. It just happens to have constant terms in both the numerator and denominator, so it doesn't look like we have polynomials on the top and the bottom. But the reason I mention that is just that everything that we've done with numerical fractions can be done with rational expressions. So we can extend all of our ideas about numerical fractions to rational expressions, depending on the way that you learned how to do operations with fractions. One of the unfortunate things about, and they've tried to change it with Common Core, but it's been a very slow transition because all the teachers that didn't teach with Common Core like don't want to change, or I shouldn't say that they don't want to. They're not being provided the professional development opportunities so that they can learn things, to teach things a different way. It's not their fault, but one of the unfortunate things about like the way this is taught traditionally is that like we learn a lot of tricks to simplify numerical fractions that don't actually work with rational expressions. So sometimes we have to back up a little bit and think about how we can simplify numerical fractions in a way that will actually translate to simplifying rational expressions. So the whole idea of like dividing the top and the bottom by the same number doesn't actually work if we extend our understanding of fractions beyond like just basic numerical fractions. So let's look at how we can simplify a numerical fraction in a way that will extend to rational expressions as well. So the way that we simplify a numerical fraction, like let's say simplify, let's start with like a really simple one, like 4/6. So traditionally we've been taught to like divide the top and the bottom by 2 maybe. It's not actually a mathematically valid idea to do the same thing to the top and the bottom of a fraction. Like for instance, I can't add 1 to the top and the bottom of a fraction and get something equivalent, right? That's just simply not true. The reason that dividing the top and the bottom of a fraction by 2 works is because what we're really doing is we're saying that 4 is 2 times 2 and that 6 is 3 times 2, and then we're actually dividing 2 by itself. We're doing 2 divided by 2, which gives us a factor of 1, and so we're saying 4/6 is the same as 2/3 times 1, and multiplying by 1, of course, doesn't change the value of anything, and so that's why 4/6 is equivalent to 2/3. So when we do that division by 2 on the top and the bottom, we're actually not dividing 4 and 6 by 2, we're dividing 2 by itself, and noting that that gives us a factor of 1. So it's sort of a trick that works every time, but not for the reason that we think it works. So this idea is of canceling those common factors to remove these factors of 1 to simplify a fraction is what we're going to use with rational expressions. And with bigger numerical fractions, it actually works a lot quicker than dividing the top and the bottom by the same thing. So like if we want to simplify like 120 over 320. Some of you might have seen this before, like we can use prime factorization. So prime factorization you can do using a factor tree, right? So 120 is like 2 times 60, which is 2 times 30, which is 2 times 15, which is 3 times 5. And like when you get really, like when you practice this a lot, you can do it in your head. Like when I look at 120, I think of like 10 times 12, right? So 10 is like 2 times 5, and then 12 is 4 times 3. So you can kind of do them in your head, like, and get pretty fast at it. But the factor tree will also always work to give you that prime factorization. It's just the ends of all the branches. And so then over 320, like 32 is 5 factors of 2, and then times 10. 1, 2, 3, 4. Okay. So then we say 2 divided by 2 is 1. 5 divided by 5 is 1. 2 divided by 2 is 1. And then 2 divided by 2 again is 1. So we end up with 3 over 8 is what 120 over 320 is equivalent to. And the reason that we like to look at simplifying numerical fractions this way is that we're going to extend the same exact understanding to rational expressions. So simplifying fractions that have polynomials in the top and the bottom. We've learned in the past week or so how to factor polynomials. So if we can factor polynomials just like we factored the numerator and denominator here, then we can cancel common factors in the same exact way. So we should, before we start doing that within the fractions, we should talk a bit more about what a polynomial looks like when it's in factored form. So we talked a bit about this yesterday, but let's go a little bit further. Which of the following is in factored form? And so what we mean by that is like it's written as a product. So we talked yesterday a little bit about this, about like the main operation is multiplication, right? So the only addition and subtraction is happening within individual factors, not outside of the multiplication. So written as a product. Oh, I don't have room. So I'll write them all and then we'll talk about each one of them. So we have x squared plus 9x plus 6. X plus 1 times x minus 2 plus x minus 1 times x plus 6. Plus 1, and then we'll do 2x squared plus x minus 9 times 2x plus 1. So what about that first one? Is that a factored polynomial? It's not, right? Because it is the sum of individual monomials, right? So that's what a fully simplified polynomial looks like, is it's a bunch of monomials, so a number times a power of x added together. So we could think of this as factored if we said the only factor is x squared plus 9x plus 6, like that whole thing can be thought of as one single factor, but we can't, there's no individual factors there that we could theoretically cancel if it was in a fraction. So that's not in factored form. I don't want to write an, I'm just going to put a line through it because I feel like writing an x makes it look like a variable. We could look back on that and not know what we mean. What about that second one? Is that in factored form? Is it a product? It is not. Why not? Yes.
The addition sign makes it two separate.
Yeah, so there's addition outside of those parentheses. So like if you're having trouble with this conceptually, like the quick thing to remember is to look for addition and subtraction outside parentheses. Like, and that's something that like you can like always just see, right? So this this addition right here makes this an addition problem rather than just a multiplication problem. So the idea is that if it's written as a product, the outside operation is just multiplication. So there is multiplication going on. We have a product here and we have a product here, but they're being added together, so the entire thing is not a product. So this one is not factored. What about that third one? Is that factored? It is not, because there is this addition here, again, outside the parentheses. So if we're just looking at it visually, we're just looking for any addition or subtraction outside parentheses, means it's not factored. But again, like there's multiplication here. It's x times x plus 3, but there's that plus 5 like tacked on. You can think of it kind of, if we want to look at it in terms of like how this affects simplifying a fraction, like if I had 5/6, I could say that like 5 is 2 times 2 plus 1, and that 6 is 2 times 3. But like I can't cancel those 2's because 5/6 is definitely not equal to 1, right? Like that's just simply not true. And it's because of this addition, right? That when I do that 2 divided by 2, that doesn't make a factor of 1 in the fraction overall. I can't call this 1 times 2 plus 1 over 3. That's just not true. None of this is true. So that's what happens. Like we can have like a factor or a product within the numerator or denominator, but that doesn't make it something that we can cancel if there's addition going on or subtraction going on outside of that product. I'm always afraid if I write down a non-example, somebody's going to write it down in their notes and like look back on it and think it was true. So this one is not factored. What about that fourth one? Is that a product? That one is, right? If we look for addition or subtraction, the only addition subtraction we find is within those parentheses. So it's happening within one of the individual factors. Outside of the parentheses, the only operation going on is multiplication, right? We have multiplication here, here, and here. And then there's no addition or subtraction going on outside of that. And so this one is a product. What about that last one? Is that a product? It's not, right? Because of this addition right here. And this is the kind of thing like we have to be really careful about, because that the fourth one and the fifth one look really similar, right? The only thing that makes them different is that plus sign. And so that's why like if we're factoring or working with polynomials and we forget to write a plus sign where there is a plus sign, then all of a sudden it becomes a product when it wasn't really a product, right? So that plus sign makes a huge difference as far as what we can do with this polynomial and what we can't do with it. So we have to be pretty careful about really watching out for what the actual operation occurring is, because that addition right there makes that last one not a product, and so it means that we can't use it to simplify a fraction. So let's simplify some of these guys. Let's start with hey, 3x squared plus 6x squared plus 2x. So the first thing I'm going to do is look at the numerator and denominator and ask myself if they are products. So is the numerator a product? It's not, right? Because there is addition between those terms. If there's addition or subtraction, I always put the entire numerator in parentheses, the entire denominator in parentheses, and those parentheses help me remember that I can't cancel anything at this point, right? So once you have a set of parentheses, the only way you can cancel is if you cancel the entire thing. So the only way we'd be able to cancel at this point is if everything in the parentheses was the same and we're crossing off both of them. So whenever there's addition, subtraction, I put parentheses around it to help me remember that I can't, for instance, cancel this x squared because that's within a set of parentheses. I can only do like whole factors. So now I'm going to factor the numerator and denominator. So in this case, I'll start with GCF. So there's a GCF of 3x in the numerator. We get x plus 2. And then I have a GCF of 2x in the denominator. And we get 2x plus 1. So the numerator has 3 factors. It has a factor of 3, a factor of x, and a factor of x plus 2. So, yes?
3x plus 1.
Oh, thank you. I'm sorry. So the 3 things being multiplied to make up the numerator are 3x and x plus 2. The only things we can cancel are if there's the exact same factor in the denominator. So the denominator also has 3 factors. It's got a factor of 2 times a factor of x times a factor of 3x plus 1. And sometimes putting those dots in helps. Because yesterday, remember, we were like, oh, we can kind of think of 2x as a single factor because it didn't affect the solutions to our equation. But here, we want to think of 2 and x as separate factors because these guys do have a factor of x in common, but we can't cancel off the entire 3x and the entire 2x, right? Because the 3 and the 2 aren't the same. So we do have to separate those factors in this case so that we can cancel just the ones that are the same. So x divided by x is 1. That's the only thing I can cancel here. So I cannot cancel, for example, the x's that are within those factors because x plus 2 doesn't have a factor of x. I can't write x plus 2 as x times something. So that entire thing is a single factor, and the 3x plus 1 is a single factor, and I can only cancel if they're the same. So this final answer is going to be 3 times x plus 2 over 2 times 3x plus 1. And the nice thing about working with rational expressions is there is absolutely no need to distribute here to get our final answer. So you can leave your numerator and denominator in factored form. And that's mostly just because we like for our answers to be in a usable form. And anytime we do something with rational expressions, the first thing we do is factor everything in sight. So if we were going to take this and use it in another problem or another step, the first thing we'd do is factor. So we might as well leave it factored so that it's easier for the next person who's about to use it because they don't have to do the factoring. In my math lab, if I've had people tell me before like that my math lab didn't accept an answer because they didn't distribute, I have strong suspicions that there was other reasons that it didn't accept the answer because I've never had it not accept an answer for not distributing. But if you think that that's going on, just send me a picture of your answer. If it is, in fact, equivalent to the right answer, I'll just give you credit for it. But if it's not, I can help you understand like where the error is and why it's not just because you didn't distribute. Because sometimes it's easy to miss the like little signs and things like that. So it's just easiest if I look at it and I can help you understand. Okay, let's do another one. Do this one. Okay, so again, that was really weird. It's back. So again, there's or in this case, there's just subtraction in the numerator and denominator. So I'm going to put the entire numerator in parentheses, the entire denominator in parentheses, and then think about factoring each of them. So remember that the first step to factoring is to put the polynomial in descending order. So, well, I guess first we should look at this and like ask ourselves if these are the same. Like, can I just cancel? They're not the same, right? Because subtraction is not commutative. Like the order matters. 5 times 2 is different from 2 times 5 with subtraction. And so I can't just say, oh, I see an x and a 6 and they both have subtraction between them, so I can just cross them off. So we have to think about factoring each of these. And the first step to factoring was always to put the polynomial in descending order, right? So we're going to make sure both of these are in descending order. The first one already is, or I shouldn't say first, the top one already is. In the bottom, I'm going to write this as negative x plus 6. And then the second thing we always thought about when we were going to factor was if we had a positive leading coefficient, so if the first term was positive, and if it wasn't, we factored out a negative to get a positive first term, right? So again, I have a positive first term in the top, but in the bottom I have a negative x. So negative x plus 6 is the same as negative 1, and then factoring that out changes both of my signs. And so this is one of the reasons that we do those first two steps. So we put everything in descending order and we get a positive first term, because then when we have common factors, they'll look like common factors. So we won't miss anything because things aren't in the same form. So now at this point, I have a common factor of x minus 6 that I can cancel. What do I end up with on the top when I cancel that x minus 6? Yeah, it's 1, right? The only way to get 0 is by adding or subtracting. Like if you subtract like 6 from itself, you get 0. But there's nothing you can multiply or 6 by to get 0 or divide 6 by to get 0 other than 0 itself. So if there's not already a factor of 0 there, there's no way that any of this is going to be 0. So this is just a factor of 1 when we get rid of everything else. And so 1 divided by negative 1 is equal to negative 1. So this whole thing is equal to negative 1. So we're going to go from simplifying rational expressions to multiplying rational expressions. And the good news about that is that they're exactly the same process. When we multiply rational expressions, we actually don't do any multiplication. We just factor everything in sight and cancel common factors. So when we multiply numerical fractions, what's the one I did? 25 over 33 times 44 over 30. So probably at some point in your life, somebody taught you to multiply 25 times 44 and multiply 33 times 30 and then simplify from there. That's actually like the least efficient way to multiply fractions, because you end up with these big, huge numbers on the top and the bottom, which you then have to like figure out what they're divisible by, so factor them or divide them by something. So it actually works just fine to just smush the fractions together and say like the numerator is the product of the two numerators, the denominator is the product of the two denominators, but then instead of actually doing that multiplication, I'm going to break each of those factors up more. So 25 is just not 2 times 5, 5 times 5. And 44 is 4 times 11, so that's 2 times 2 times 11. And 33 is 3 times 11. And 30 is 3 times 10, so that's 3 times 2 times 5. And none of those was super difficult to factor, right, because we use the smaller numbers, whereas if we had multiplied 25 by 44 first and then tried to factor that, that would be kind of a pain. That's a really large number. So now I can say 5 divided by 5 is 1, 2 divided by 2 is 1, 11 divided by 11 is 1, And then this simplifies to 10/9. So we didn't actually have to like do the multiplication in order to multiply these fractions. We just had to like just smush. It's a very complex mathematical operation. Smush them together. And that's what we're going to do with rational expressions. And remember, with rational expressions, we don't even have to multiply at the end. We just leave it factored. So you literally don't do any multiplication when you multiply rational expressions. Like, all you do is factor and cancel. So it's a little misleading because in the instructions in your homework, you will see something like this, where it'll tell you to multiply. And like, so it's going to say multiply, but you don't actually want to do any multiplication here. In fact, like, so with this example, it's true that you could multiply 25 by 44 and then break that down, and you'll get the right answer. It's just quite time consuming. When it comes to rational expressions, if you actually multiply the numerator and denominator, the possibility exists that you will end up with a polynomial that we haven't learned how to factor. So like if you do the multiplication first, like you won't even be able to break it down because we haven't learned how to factor every single possible polynomial. So if you end up with something big, like something with 5 terms, like we've only talked about 4 terms, 3 terms, and 2 terms, right? So it's extra important that you don't actually do the multiplication here because you don't want to end up with something that you can't break down again. So we're going to say if there is, just like before, if there's addition or subtraction in our numerator or denominator, we're going to put the whole thing in parentheses. And so then I can write this as a single fraction just by smushing my factors together. So this is x plus 2 times x squared minus 2x minus 3 over x minus 3 times 4 minus x squared. And from here, I want to factor. So from here, I'm just simplifying the same way we simplified a single fraction before. We just have 4 things to factor instead of 2. And kind of organizing your work on this is one of like the biggest challenges because it's easy to get lost in everything that's going on. So I kind of like to like make like this little window pane dealy. And that way I can be like, okay, I have like a top left and a top right and a bottom, a bottom left and a bottom right. And then you can do like your factoring within that and like everything's still in place so you know where to put things back when you put them back into the fraction itself. So x plus 2 can't be factored. X minus 3 can't be factored because those are linear already. So those are just done. And then I can use the AC method to factor x squared minus 2x minus 3. I'm going to use shortcuts at this point in class just so that we can spend our time on like the new concepts and not spend our time on the actual factoring. But that doesn't mean that I think you should all be using shortcuts. Like keep factoring the way you've been factoring until you can do it quicker. But I promise I won't lead you astray. This factors as x minus 3 times x plus 1. And then in the denominator there, so on the bottom left, I'm going to put that in descending order. I'm going to get a positive first term by factoring out a factor of -1. And then this factors as x plus 2 times x minus 2. And again, I'm not by any means saying that you have to do all of this in your head. I'm just saving a little bit of time so we can focus on the actual concepts that are new rather than spending all our time on factoring. Because really, most of this chapter is really just factoring. We're adding one little wrinkle to it in that after you factor, you cancel things that are the same. but for the most part, like we're still just factoring a bunch, is the bulk of the time that you'll spend on these problems. So now we're going to put everybody back in its place. So top left is x plus 2. Top right, we're going to replace with x minus 3 times x plus 1. Bottom left, we're going to replace, or is still x minus 3, I guess. And then on the bottom right, we have to be a little bit careful, because if we just write it the way that we wrote it over there, like so, what operation is this right here?
Subtraction.
It's subtraction. And what operation is this right here?
Multiplication.
Right, I don't want to change that operation from multiplication to subtraction. So anytime there's something to the left of a negative factor, we have to put that in parentheses to show that we're multiplying by -1. We're not subtracting 1 times whatever. And if you find yourself like making that error, just go ahead and put it in parentheses, like to begin with. And that way, like, even though we're used to like just like having those monomial factors not in parentheses, if you are putting it back into a bigger expression, sometimes it helps just to leave it in parentheses so that you don't accidentally call it subtraction. So now I'm going to go through, now that everything is factored, I can go through and I can cancel any factors I have in common. And in this case, it turns out that we have just an x minus 3 and then an x plus 2, and then that's all I can do. I cannot cancel these x's because they are within factors, right? They aren't factors of their own. So in general, like just a good general rule is don't cancel anything that's inside parentheses unless you're canceling the entire set of parentheses. So like if that's all you remember from all of this, then that's probably enough. But you just have to make sure that you put things in parentheses that need to be in parentheses. So this is x plus 1 over -1 times x minus 2. And when there's only one factor in the top, like you can lose these parentheses like in your final answer on the top. But if it helps you to have them to like help remember not to cancel anything, my math lab will accept it either way. Like they don't, either in the parentheses or not in the parentheses. If you don't think so, then send me what you're talking about. But I promise that I've been doing this for a few years and they take it. I've tried it a bunch of times. They're like, I've seen every once in a while like that they want you to distribute this -1, and it's just like some weird like order stuff. So again, like if you think that all it is the way you're entering your answer, all you have to do is send me a picture of it. Or you guys have used that Ask My Instructor thing. Have you seen that? So if you go to the question help tab in any question and select Ask My Instructor, you can it sends me the question like right from my math lab. So it's like, because everybody has different questions, like it generates different numbers for everybody. So if you use that to email me, it's a really quick way to be like, hey, this looks like it's right, what's wrong with it, or why is it marking it wrong? And then if it really is a formatting thing, I can just give you credit for it. But that's a really quick way to send it to me so I can check. And it shows me your answer as well. So that's our final answer. We're going to move on to dividing, which again, it sort of feels like we're doing a lot of things. Like we simplified, we multiplied, now we're going to divide. But they're all exactly the same thing, really, because when we divide fractions, we rewrite it as multiplication, right? And then we're right back in the same situation that we were in when we were multiplying. So if we have division, and again, they use these words like divide when we're not actually going to do any division. We're going to rewrite this as multiplication by the reciprocal of the divisor, and then we're going to factor and simplify. So let's do this guy. So again, I'm going to start with putting my numerators and denominators in parentheses. And then we divide fractions by rewriting as multiplication by the divisor. So the divisor is the thing that you're dividing by. So it's always that what comes after the division sign. So I can rewrite this as a squared minus 1 divided by a minus, I shouldn't say divided by, over a minus 1 times a squared minus a over a squared plus 2a plus 1. And now we're right back where we were in the last problem. We're just multiplying. So I'm going to go ahead and just organize my work a little bit to factor everybody. So we've got a squared minus 1 on the top left, a minus 1 on the top right, a squared minus a, and then a squared plus 2a plus 1. So a squared minus 1 factors as a plus 1 times a minus 1. A minus 1 is a linear factor, so it doesn't factor anymore because there's no GCF to pull out. And then a squared minus a has a GCF of a, so we have a times a minus 1. And then a squared plus 2a plus 1 factors as a plus 1 times a plus 1. So now I'm going to put everybody back in their place, one big fraction, and we have a plus 1 times a minus 1 times a. And I don't have to put that a in parentheses in this case because it's not negative, so there's no risk of me mistaking that for addition or subtraction rather than multiplication. Although if you put it in parentheses, it's not going to hurt anybody. And then in the denominator, I have a minus 1 times a plus 1 times a plus 1. So let's see what's the same. We've got a minus 1 divided by a minus 1. We've got a plus 1 divided by a plus 1. And then that's as far as I can go, right? Because the numerator has a factor of a and a factor of a minus 1. The denominator has a factor of a plus 1. They don't have any common factors. So we end up with a times a minus 1 over a plus 1. And we're done. And again, that a plus 1 can have parentheses or not have parentheses because it's the only factor. But either way is fine. I find that people are less tempted to cancel that a if they leave the parentheses in the denominator. So if you start making the mistake of canceling things that shouldn't be canceled, I'll probably tell you to keep your parentheses just for your own good. But, let's see, 9:43. Oh, I think we have time to do one more. We should do one with 3. So let's simplify. These mostly, the challenge with these problems is they mostly look a lot more complex and scary than they are. Like, it looks like a ton is going on, but in reality, all you're doing is factoring and then, like, crossing some stuff off. So try not to be intimidated by how complex they look. They take a little bit of time, but it's all stuff that you've done before. So over y squared plus y minus 2 times y plus 3y plus 2 over y squared plus 4y plus 4 divided by y to the 4th plus 1 over y squared plus 2y minus 8. And they are somewhat time consuming, I'm not going to lie. Like, it takes a bit to factor all of these. But again, we're just going to start with parentheses around all our numerators and denominators. Then we see that there's division here, so I want to write this whole thing as multiplication. The only thing you take the reciprocal of is a fraction that is immediately following a division sign. So in this case, we need to take the reciprocal of this guy. It wouldn't matter if they're, like, we could tack on, like, times something else, times something else. The only one you take the reciprocal of is the one right after that division sign. So we have y squared minus 2y over y squared plus y minus 2 times, oh, I'm sorry, this is supposed to be y squared plus 3y plus 2 over y squared plus 4y plus 4. So those ones I just copied. And then I'm going to multiply by the reciprocal of this guy. So 2y minus 8 and y to the 4th plus 1. Now one big line, and I'm going to factor everybody in sight. And again, like, do your factoring over on a separate part of the paper or even on a separate sheet of paper and just organize enough to remember like where to put things back into the fraction. I definitely don't expect you to do all the factoring within like this whole thing. That can get pretty messy to try to like factor like within that big fraction. So, but I'm just going to do it in my head in the interest of time. So y squared minus 2y factors as y times y minus 2. Y squared plus 3y plus 2 factors as y plus 2 times y plus 1. Y squared plus 2y minus 8 factors as y plus 4 times y minus 2. And then we have y plus 2 times y minus 1. Y plus 2 times y plus 2. Does y to the 4th plus 1 factor? Why not? Right, it's not subtraction. Remember, those binomials only factor if there's subtraction between the terms. It gets really tempting when we start to get moving on these guys and do the factoring pretty quickly. It gets really tempting to factor things that don't factor, so really be sure that you're aware of that rule about factoring binomials. It has to be subtraction for there even to be a chance. So now we are going to, let's see, slash and dash. So we have a y plus 2. Oh, there's not much here, is there? That's it. Nothing else is the same. We have no y minus 2's on the bottom. We have no single factors of y on the bottom. We have no y plus 1's on the bottom. We have no y plus 4's on the bottom. We have no y minus 2's on the bottom. So even when it looks really ugly and messy, we can't force it. So this whole thing, you can use exponents to condense things a little bit. So we have y times, there are 2 factors of y minus 2 on top, so I can write that as y minus 2 squared. That took care of this guy, and this guy. And then I have y plus 1 and y plus 4. So that guy and that guy. And then on the bottom, I've got y minus 1. And then there's 2 factors of y plus 2. And then that y to the 4th plus 1. And that's just done. As ugly as it is, sometimes it ends up ugly. But we have to factor everything to figure it out. So again, your homework tonight, if I can get it, there it is. So 5 plus 1, we got to go, so we won't worry about that. There weren't that many anyway. You guys will be at the top of the pile tonight, so you'll get plenty tomorrow. And I will see you tomorrow. Have a great afternoon.